Go ahead.
Okay, cool. Yeah. Thank you, Jidin. So I just want to introduce myself real quick again. Uh, I'm Shaolun, and I'm in SMU for now. And I just graduated from USDC in China in 2019. And my research interest is about data visualization, human-computer interaction, and some other applications like quantum computing, bioinformatics, etc. Maybe also including the immersive analysis. Yep. And a lot of people ask me about what is your major before you just pursuing your PhD. Uh, I'll say like yeah, I'm studied the data visualization, but I'm just studied the application-based data visualization. So that's why I just wanna focus on the quantum computing. This domain, I think, this domain is still underexplored, and it is a big chance for the data visualization to do something in this direction. Yeah. So let's go ahead. Just yeah. So this is the title of today's presentation, which is the witness the new era of quantum computing. So so in this topic, I just want to introduce something about my own work and my own understanding of this new direction, which is the visualization for quantum computing. So let's get started. The quantum computing and its devices, quantum computers, has shown a considerable speed up over the classical counterparts you may already know. And at the same time, there are literally over 15,000 quantum computer physics which are wanted in the US in 2015. And meanwhile, it's around 90 different types of new jobs for the quantum computing commercial job in 2018. And there are many CEOs of quantum computing companies, which they just point out that there's like a huge gap to training the quantum computing scientists and hiring them. Yep. And uh, as you can see, the gap for hiring the quantum computer scientists and the needs to train them is very large. But the point is, uh, it is not that easy to learn quantum computing and further achieve the so-called quantum advantages because many just articles, report, and some research papers just point out that this is because the quantum computing got a very, very steep learning curve. So that's the reason why I just want to apply the visualization to for the quantum computing because uh, the visualization in itself has been proven to be a uh, very good scientific education tool to educate people to learn what is quantum computing, how it works, what is the inner workings of the circuits, so on and so forth. So I'll just start with my four of my works, and this four works is basically about the visualization for quantum computing. But there are some differences between them because for the first one, which is noise awareness in IBM quantum, it's like a workflow for the users of the IBM Q platform. And this work is just, it's not used to explain what is the circuit, how the quantum state evolutes. It's just for the users to and make the noise hidden in some, the qubit and quantum devices, make it more transparent and make the workflow of the execution more smooth. And the rest of the three works as shown here, the first one is quantum state visualization. So we move a little bit forward compared to the previous one. And we focus on how to visualize the quantum states. And then for the third work, we just move a little bit further again to focus on explain what is a quantum circuit. And at last, which is also our most recent work, we studied how to visualize the quantum neural network, which is a brand new application in the quantum computing, and it is very popular. So that's why I think there's need to study it and make it more easy to understand for the novice and users. So for this 4 work, we published all of the 4 works. I'm sorry, I published all of the 4 works to the top conferences in the visualization field and human-computer interaction. Those conferences listed here, HWVs, EuroVis, HWTVCG, they're all both top conferences and journals. So I'll start with the first one, which is called vaccine or visualization approach for noise awareness in quantum computing. So this work is collaborated with my amazing collaborators from George Mason University, Fordham University, and Kent State University. So for now, you may already know we are at the stage of the NSQ era, which is a noisy and intermediate scale quantum, which means the noise is very severe. It's a very severe issue, and at the same time, it is inevitable in today's quantum computers. And after the analysis of the noise hidden in quantum computing, we just group them into 2 categories, which is the noise from quantum computers and the noise from the compiled circuits. And at the same time, there's no visualization tool to reveal those hidden noise in quantum computers and compiled circuits. And for now, I just want to briefly give you some examples of what is the noise from quantum computers and compiled circuits. So for the first one, quantum computers, it means that there are some different types of noises hidden in quantum computers, like T1 time, T2 time, which is the coherence time or something else, and maybe the error rate when you measure the qubit, when you measure the signal gate. They're all got some noise in the quantum computer naturally. And what is the noise from the compiled circuits? It means that it's like if you try the IBM Quantum and the QuizzKit by yourself, you may find that after you transpiled your logical circuit, it will be transpiled into, like, if you transpile it like 100 times, and the transpiled result will be different, 100 different types of the logical circuit. Oh no, I'm sorry, physical circuit, and their topology is totally different. So each types of the transpiled circuit or compiled circuit, they contained different levels of noise. So that's why we just group them in as the second category, which is the noise from compiled circuit, because of the differences of the topology of the compiled circuits. And so to address this issue, we need first allow users to select the quantum computers before the real execution, based on their metric of the noises, like the coherence time, error rate for the qubit, and some other types of gates, and so forth. And at the same time, we may make it more useful to allow these users to select their preferred or optimal compiled circuits in terms of the noises hidden in each of the transparent circuit. And this task must support the real-time compilation because the matrix of the noise just changed very quickly. So if you use the record of the noise like yesterday's, it doesn't make sense. So we must make it as a real-time tool to support the users to reduce the noise hidden in their transparent circuit. So here is the system we proposed. We proposed a visualization system called vaccine, which is we named it because we just finished this work during the COVID. So we just wanna use this tool to fight against the noise. And here's the module of our system. We use data storage, and we got a processing module to just process the raw data and some calibration data from the IBM Q platform. And we also got some visualization approach to visualize the noise, like as shown here, the computer evolution view, which is for the quantum computer selection, and some other views like circuit filtering view and circuit comparison view, which are for the compiled circuit selection. And we connected our tool to the remote quantum computing platform, which is IBM Q, to support real-time execution, real-time compilation, so on and so forth. Okay, so I just want to introduce this work real quick. So let me summarize this work very quick, which is we first develop a tool to make the IBM Q users aware of the noise in the quantum computers. So this can lead into the uncertainty can be just mitigated in real time for those IBM Q users. So this is the first work, and we just published it to the conference of IEEE last year. It's a top conference in the visualization field. And then our second work about the visualization for quantum computing is called the Venus, a geometrical representation for quantum state visualization. So, and you see, it's just such a long of the list, right? And this work is also in collaboration with my collaborators from University of Delaware, Kent State University, HKUST, Fordham University, George Mason, Brookhaven, and also my supervisor. This is my supervisor, by the way. Okay, and we already know that quantum computing has a limited interpretability for users to use, and many papers just proven that the quantum computing is very, very counterintuitive, and it's very abstract and very hard to understand its mechanics. And specifically, it is important to visualize the quantum state with more than 1 qubit, which is the basic requirements for quantum entanglement, of course, because the entanglement itself, it requires at least 2 qubits, right? But for now, I think the most commonly used approach is the Bososphere, and Bososphere just it can just only support 1 qubit, as you already know. And second, it is important to visually explain the measured probability of basis states. So for example, if probability of state 0 is let's say 0.5, and the other state, the state 1 is also 0.5, but why is that? Why is the probability of the two state just is around 0.5 at the same time. So the users may got no idea how to understand this probability, this measured probability. So to this end, oh no, I'm sorry. Before that, I just want to introduce the Bossphere real quick. And Bossphere, as I mentioned before, it is the most commonly used visualization tool to visualize the quantum state for single qubit. So that's why this is the first major limitation of it, which is it can only support 1 qubit. And at the same time, it is non-intuitive to represent the probability. Just like I said, when no, I mean when the probability of the two states, state 0 and state 1, is shown on the Bossphere, but it just a point on the sphere, right? You cannot just observe the probability based on like its height or its location, so on and so forth. You cannot just observe it directly through the Bossphere. So it is non-intuitive to represent the probability, even though you can, even though the Bossphere, it is very effectively to be used for for visualizing the quantum state, but the measurement is not intuitive. And the third issue is that because the Bossphere is actually a 3D models, right? And many research papers and many like evaluation papers, they just evaluate that the 3D models, it is very ineffective to show its measurement on the Bossphere on the 3D models via the 2D screen. So if you are you just wanna observe some states or some points on the sphere back and forth, you may not just accurately to perceive the measure on the axis. So based on the based on the three issues, we just propose a VNS, which is which can support the visualization for single qubit and 2 qubit states. Yeah. So as you can see, compared to the Bossphere, we just move a little bit forward to make it support the 2 qubit states. And at the same time, the VNS itself can visualize and explain the measured probability. And later, I just wanna briefly introduce how it just visually explained the measured probability. And here is the design of our visualization VNS, which is for the single qubit case. So in this case, as you can see, it can visualize the state phi as shown here, which equals to alpha plus state 0 plus beta plus state 1. And I just introduce its geometrical principles one by one. And first, as we already know, the alpha and beta, which is shown here, they are the amplitude of this quantum state. And amplitude alpha or beta can be just they equals to the A plus B multiply I, which is the imaginary part, or imaginary unit, I'm sorry. B is the imaginary part. And C beta equals to C plus D multiply the imaginary unit. So alpha and beta, they are all the complex number, right? So based on this formula, we just simply encode the A and B as two sides of these right triangles as shown here. This left segment indicate the absolute value of A, and this like segment just denotes the absolute value of B, and same for the amplitude beta, and shown here. And at the same time, after this encoding, we just give two half semicircle at the outer space of the A and B and C and D, which the reason why we do that is that if we just encode the area of the semicircle like this, which can be written by this formula, right? The A and B is the intersected light segment A and B, and the area of it can be written like this. But at the same time, based on the quantum mechanics, the probability of state zero. This one is for state zero. The probability of state zero equals to the square of alpha, which equals to the sum of the square of A and B, right? So by combining these two formula, we can see that the probability itself is like proportional to the area of the semicircle. So why we would do like this? Because when these two just is proportional to each other, in this way we can just observe we observe the probability of zero by observing the area of the semicircle. So that's why we'll do that. We encode the probability of state zero into the area of the semicircle, as shown here. Okay, so yeah, and we also just encode the constraint. The constraint, like what is the constraint, by the way? It is a sum of square of alpha and beta, which is exactly the base side of this large triangle, right? Because for this one, I think it makes sense, right? For the probability of zero, which is indicated by the square of alpha, and the probability of state one, which is represented by the square of beta, the sum of the probability will always equal to 1, right? So this side represents the square of alpha, and this side represents square of beta. So yeah, the length of the base side will always be 1. So based on this formula and based on this encoding, we can just observe, or we can just validate or confirm if the equation is correct. Because if it's not correct, I mean, if some parameters like C or D is just incorrect number, the base length will not just keep as a length of 1, right? Yeah. So this is very encoding for the single qubit case, and this is the visualization for the 2 qubit case, which is in the same principle, design principle, which we just extended two right triangles based on the original one. Yeah, as you can see, this is the original right triangle for state zero, right? So we based on this, we just extend 2 more for each right triangle here. So because the state for the 2 qubit case, the number of the basis state will be the power 2 of 2, right, which is 4. So we got 4 semicircles to represent the probability of the 4 basis state, which is the state 0, 0, 0, 1, 1, 0, and 1, 1, respectively. Okay, so yeah, and the encoding is exactly the same. So based on this one, you can also observe the probability of each basis state based on the area of each semicircle. So for now, I'll give you a simple example real quick to illustrate how it works. So I'll just use a quantum classifier case to demonstrate our visual design. And this classifier is based on the iris data set. So this is the 1-qubit quantum neural network and also the quantum classifier. And for the encoding layer, it is consists of the RY gate and RZ gate. And for the ansatz, it contains RY gate and RZ gate as well. So yeah, for this QNN, we just randomly pick out one data point. And for this data point, as you can see in the subfigure 1A, this is in epoch 1. And this data set looks like this. This data point, I'm sorry, looks like this. It got two possible basis state, which is state 0 and 1. And for the state 0, it got 69% of the probability to be state 0. And for around like 31% to be mirrored to state 1. And after a while, in epoch 25, it becomes something like this. You know, the probability of it just reduced because the area of the semicircle just shrinked compared to the previous one. And we can see that this is because the imaginary part just reduced compared to the previous one, which leading to the decrease of the merit probability. And as you can see in the epoch 50, this one, the probability of state 1 become larger compared to the previous two subfigure. And we can just see the reason. Oh, sorry. We can just see the reason of this increasing because the real part of the amplitude beta just increased. So the total merit probability increased based on the increase of the real part of beta. And it remains the same after the 50 epochs compared to the previous subfigure A3. You see, it just remains the same. So it probably like this QN has converged after the epoch 50. So as you can see, we can just directly observe the probability based on the area of the semicircle, right? And we can also just find the reason of find the reason why the probability of the state increase or decrease by just like inspecting the length of the segment inside each semicircle. Okay, so the future work of this paper is that we need some more automatic approach to input the state vectors into this visual design to make it more smooth for users to use. And we also need to address the scalability issue of the qubit numbers because obviously it can only support 1 or 2 qubit, right? So it is expected to be to support more qubit numbers. So yeah, this is what's new. And so what we propose a novel representation VNS, and to try to explain the merit probability based on the amplitude for both single and 2-qubit states. And let's move on to our next work, which is called Quantum Eyes, toward better interpretability of quantum circuit. So this work is it is obviously it is based it is for the visualizing the quantum circuit, and which is the static quantum circuit basically, because it just does not contain any trainable parameters inside it. And maybe you still remembered the limitation of my previous work, which is the scalability issue, because of just my previous design can only support 1 or 2 qubit, right? So this work we just extended to like infinite number of qubit. So before that, we just like we perform a real short brainstorming. So here's the question: how to visualize the quantum state which can satisfy the number of the data entity is very large. Let's say it's around or more than 100 data entity inside this visual design. And at the same time, we focus on those data entity with large merit probability. And second, it can just explain the probability based on the quantum mechanism constraint, which is also used to explain why merit probability is just that number. Okay, so keeping these two questions in mind, we move forward. And so for now, I just want to briefly introduce how our design addressed the scalability issue of our previous work. So this is called the dandelion chart. Why we will call that name, I will just explain it later. So before that, we just take a look at this very coding. So first, we use based on these two constraints, as I mentioned before, which is the formula for state vector, and the other one is the probability distribution equation, which is used to calculate the merit probability based on the state vector as shown here. So the quantum mechanism constraint is exactly the same compared to my previous work. But in this design, for example, we just use a complex ordinate system, which is used to just locate the real part and the imaginary part of each quantum states into this figure. And based on this one, we just draw a circle using using the length of this last segment, and we draw a circle as shown here. So for this case, we use a 2-qubit case, and so we got 4 basis states. So as you can see, we got 4 points and shown here, and each point just represent a basis states. Like this is like state 0, 1, so on and so forth. And after we draw a circle using with a radius of each last segment, we can easily get that the area of this circle can be represented, can be used to represent the probability of state like state 0, 1, because the probability of state 0 is proportional to the area of this circle, right? So this is a very simple formula to calculate the area of the area of the circle, and at the same time, the probability can be just written by the square or the sum of the square of A and B, right? So based on this, we can so from now we can just observe the probability of state based on the area of the circle. But based on this principle, we can easily find that there's a very severe virial clutter in this design, right? Because when you just for 4 points in this figure, we need to draw four circles using each of the points, and you can see this purple one just overlapped onto the green one, the red one, and the blue one. So how to just mitigate and how to address this virial clutter? We just simply reduce every circle, every every area of the circle by a same factor. So why we'll do that? Because when we reduce the area of each circle by a same factor, the principle just remains the same, because we just multiply a scalar. We just multiply a fixed number, a constraint before this equation. So this visual design just remains the same, because because it is the constraint number, and the probability of the merit probability is still proportional to the area of the circle. So that's why we will do that. Why we will use a fixed number to reduce each circle inside this figure. So as you can see, we just reduce it as half of its original radius, and the virial clutter just reduced a little bit, right? And we just keep going, and we keep going, reduce the radius, and as you can see, these four circles just take apart from each other. And in this figure, this is what we call the dandelion chart, because it's very looks like a dandelion. Yeah, because each basis stage is very like a dandelion, right? So in this figure, first we use the location to locate the real and imaginary part of the amplitude, and then we just encode the probability of we just encode the measurement probability by the area of the circle. And at last, we reduce the virial clutter. We reduce the overlapping of different circles by just reducing the area of each circle. Okay, so let's moving on. This is the system of this design. We use the dandelion chart as shown here to support the before and after analysis for the quantum gates of interest. As shown here, we just wanna see what happened before, or what happened after this Hartmann gate. We can just simply click this Hartmann gate symbol, and it can just show the visualization of the quantum state before and after. And so for top view, we just visualize how the probability of each basis state evolve along the quantum circuit. So it's like an overview of this evolution of the quantum state. And then based on the observation of this view, we can further perform the analysis based on the state evolution view as shown here. And this view can just visualize how the quantum state is evolved, and we can just conduct the traceback analysis based on the highlighted line in this view. And we can also click the gate symbol to show the dandelion chart before and after to see what is the effect of this quantum gate. So just briefly summarize this work. We propose a system which I shown just now, and we also propose a novel representation to visualize the n-qubit quantum state. So the users can just can easily get a sense of how the quantum state evolved from the beginning to the end of the circuit, and what's the effect of the each quantum state based on analyzing the dandelion chart. Yeah. Due to the limited time, I just wanna introduce this work real quick, and this is our last work about the visualization for quantum neural networks, which is called Violet. And this work is also published to the IEEE TVCG. And so this is the architecture of the QN, as you may already know. So it consists of encoder, ansatz, and merriment. So in short, we just visualize each of the components and shown here, and visualizing each part to make the learners, novice, more easy to learn what patterns has been learned by the model and how the measurement conducted. So basically, this is our first design, and it can first support the reflection of the learned features, just like the classical NN. So as shown here, if you can just have a glance of this figure, you can easily get what features does the model learn, and the confidence of this learning process. Like the confidence is very high at the edge of this feature map, and the confidence is relatively low at the middle of this heat map. And at the same time, when you zoom in, it can also explain the measurement. Based on this two equation, we just explained the measurement. And meanwhile, we just preserving the nature of the visualization of the learned featured, just like I mentioned before. So due to the time, I will not go in that deep. I just give you a rough sense of what it is and what it's used for. And this is our second design, which is used to visually correlate the qubit state and quantum state, because the polyrotation gate, it operates on the qubit state, right? So we just correlate the qubit state with the basis state, which the basis state is used to reflect the measurement and reflect the final prediction, the final classification of the results. So yeah, we just use this design to correlate these two things together and make users to easily understand what is the effect of the polyrotation gate made to the final prediction. So if you are interested in it, you may take a look at our papers, and I will release it to the archive platform. Yeah, so this work, we just propose a visual analysis system to help people visualize the quantum neural network. And this can allow users to easily illustrate, and they can grab the inner workings of the quantum neural network. Okay, so this is the four papers we just studied, and from now I just wanna give you a rough idea about what is the future of visualization for quantum computing in my mind. So yeah, as you can see, we received a very positive feedback from the reviewers of in the previous previous submission, and they all agree that this direction is brand new and it is very worth to explore in the visualization community. And yeah, and this is the why I call it a blue ocean, because uh, as I already know that we are the the leading group of this direction, but there are still a great number of topics which is underexplored, like the application-based visualization for quantum computing, which we can target to the quantum finance, quantum chemistry, some of the first, and we may also cover something like combining the quantum version with the classical deep neural network, which is QCN, QGAN, or QRN. And we can also do some user interaction enhancement because this is the reason of it is that I found it the tutorial and the description in the online article. They are all very not that easy to get what they want to do, and I need to just approach into the papers, but which is more difficult tasks for me. So we may do some document enhancement to make the learning of the quantum computer more easy, right? And we can also transfer the non-intuitive QSM code to graphical representation, which is more like the software engineering tasks. Yeah, and then we can also focus on the explainability issue for the quantum specific some angles like the parent plateau, the QN expressibility, so first, and we can also just apply some traditional inspired ideas to the quantum version. Yeah, and also some immersive analysis for quantum computing, which we can use some VR AR glasses. We can use some virtual objects to help people to understand the quantum computing and educate the learners with the real world objects, right? Okay, so yeah, in 2016, the visual analytics just step into the era of deep learning. But for now, just let's embrace the next generation of visualization community, which is the visualization for quantum computing. Okay, so that's all for my presentation. And if you are interested in my work and if you just want to collaborate with me, you can just scan the QR code at the bottom right and just contact me. Yeah. So, okay. Yeah, that's it. Thank you.